Hello everyone, welcome to Applied Fourier Analysis. In this video, we are required to find the steady state solution of u. So basically by the steady state, we mean that the value of u is not changing over time, right? Or temperature is not changing over time, and hence the derivative of u in terms of t is going to equals to 0 because there is nothing that is changing, right? And so we're given this over here, and then we're going to take into account the fact that this is equals to 0. So this equation was transformed to this one by setting the derivative of u in terms of t to equals to 0 over here. So we took that into its standard form, right? And this standard form is much more familiar to us, especially when we do separation of variables, right? And then the standard form is going to yield a simple harmonic motion that we have here. So it's C1 times the cos of something plus C2 times the sine of something. And then I want you guys to take note of the coefficient of u right here. So we've got that coefficient, but when it comes into the trigonometric expressions, it's going to be the square root of that. And remember, guys, that sometimes we would say lambda is equals to alpha squared. But when it comes under cos, it would be alpha x. You guys recall that? So take note that even here we took the square root of that, right? And then we imposed the conditions that were given, the derivative of u, right, in terms of x. So we derived u over there. This is the derivative of u in terms of x. And then after, we placed 0 in the position of x. And then, okay, so if this is the derivative, and then we place 0 in the position of x, in other words, sine of whatever this constant is times 0, that's going to be sine of 0. So this equals to 0. So our equation is going to be simplified further. But take note that cos of 0 is going to equals to 1. Okay, so basically this portion is 0 because of sine. And then this portion is going to equals to 1 because of cos. You know what I'm saying? So now our equation takes this form. So a is equals to c2 times the square root of alpha over beta times 1. This one was a result of cos of 0. And then here we solved for c2. Our c2 was a multiplied by the square root of beta over alpha. And then we took our c2 back into our equation. There's our c2. But now it's in terms of a, beta, and alpha, right? And then we imposed the second condition that we had over there, where in the place of x we put L. That is going to result in u equaling 0. And then we did that. Okay. And so what we did, we subtracted this portion on both the left-hand side and the right-hand side. And then now C1 was cos of the square root of alpha over beta times L is equals to minus a times the square root of beta over alpha times sine of the square root of alpha over beta times L. And then what we did, in order for us to remain with C1 here, we had to divide by cos. And then we recognized that sine of theta over the cos of theta equals to the tangent of theta. And then we saw that expression here. And then our C1 now shifted, or our C1 was simplified to minus a multiplied by the square root of beta over alpha times the tangent of the square root of alpha over beta times L. And then this whole white portion is our C1, right? And then this here is our C2. You know what I'm saying? And then what we did now, we just factored out a and the square root of beta over alpha in this whole expression. And then after we did that, we landed to the white portion over there. And this is the expression, right, of the steady state solution of u. Do stay blessed and enjoy the rest of your day.